Hello everyone. We are now embarking on the last unit of CS 372. So we started off with time-domain audio processing. That was just treating audio like an array. We then moved on to learn about the Fourier transform, which is a very powerful tool, putting on a different pair of glasses and looking at the same information through a frequency lens. Then we started to use the short-time Fourier transform as the input to a bunch of other things that we designed by hand to do all sorts of stuff. Everything from beat tracking to the Shazam algorithm for audio fingerprinting, to a little bit about music structure, cover songs, and then unmixing, right? But in each of these cases, we went in with some notion about what it is we were looking for, and we came up with a mathematical model by hand for how we would pick up on that. So for example, when it came to beats, we designed something called an audio novelty function, and we said, okay, we're going to do this because we think that a beat shows up as a vertical line in the spectrogram. And so then we will mathematically define a function that picks up on vertical lines. And everything pretty much followed that way, this whole unit. We're now going to shift a little bit to a more, people would probably say a more modern approach in some ways, which is a data-driven approach. So rather than going in with a handcrafted model based on some observations, we're going to allow the computer to learn something from a bunch of data that we give it. So we're not going to go in with an exact idea of the functions that we're going to define to pick up on different musical attributes. Instead, we're just going to start with a bunch of labeled information and have the computer pick the right function for us. And so that's a very broad way of saying something called supervised learning. And I'll unpack that as we move forward. Now, there are many ways to do this, and it's an idea that's been around for a very long time. Recently, another specific idea that's been around for a very long time, known as neural networks, has become very popular and has shown a lot of good results in a lot of areas of multimedia, particularly music, recently. So I'll be focused on neural networks primarily. But I just wanted to say that's not the only way to do data-driven approaches. There are many other ways to do this. In fact, just for one list, if I go to scikit learn, there's a whole library in Python of different ways of doing machine learning, you could say generally, is the field that we're diving into now. But I'm going to be focused on, again, this particular kind of learning using neural networks. Okay, so let me define supervised learning a little more carefully. And I'm going to start with binary supervised learning. So what I'm going to do is give you a collection of data, and each data point has a label, either 0 or 1. Okay, so there's two classes, two categories that the data could fall into. And so here's an example with some animals that you may or may not recognize. For example, there is Dr. Casey Schwartz and physics dog Pilgrim. Here's my cat Layla. Here's Dr. Sadowski's dog Uri. And there's my dog Theo. Those are my brother's cats, Artemis and Apollo. That is my best man's cat Amelia. And then this is my my in-laws cat Violet. Okay, so anyway, here are the problem. So it's actually a bit simpler than saying what their identity is. You could consider that to be a class, but we're going to make it a little simpler and say, is it a cat or a dog? Just from these images. And so we will arbitrarily choose a dog to be represented by 0, and we'll choose a cat to be represented by 1. Okay, so that's the problem we're going to look at. So I wanted to give a concrete example of binary supervised learning first. But let me do a much simpler numerical example to start with of just numbers on the number line. All right, so what I'll do is create a synthetic data set of a bunch of numbers labeled 0 next to or interspersed with another bunch of numbers labeled 1. Okay, so what I'll do is I'll just make this array x. I guess I'll say first, I'll say np.random. Let me seed it just so I get the same results each time. And actually, let me make this code a little bit bigger too. Okay, good. So what I'll do here is I will make, let's say, 50 of each type. I'll say np.random.randn, that number n, 50. Let's see, maybe I'll subtract 1 from the first group, and then I'll concatenate, okay, and then I'll say, and I have my data, so x is my data, and then I'll also have a parallel array called labels, and I'll say, okay, I'm going to label the first 50 elements as 0, and then I'm going to make another 50 elements, and they will be 1. And so what I'll do, I'll generate the same number of elements, but I'll move them over a little bit in that direction, and then I'll make sure to add the labels of 1. Okay, so let's just take a look at what that looks like there. So I'm going to just scatter them on the number line. So I'll scatter them like that. And I will also, I'll put them on the number line so they'll have a height 0. And then I will also color them according to their label. So let's have a look at what that looks like. Okay, so what we observe in this example is that the data points labeled with a 0 are further to the left generally than the data points labeled with a 1. But how would we train a computer to recognize something like that? That's the goal. We want to, from this example, train the computer to extrapolate and to say, hey, if I place something, around -1.5, well, it should probably tell me that that's most likely a 0. Okay, so that's the goal of supervised learning, to learn from examples. So let me kind of specify the strategy a little more precisely, but still in a general way. So here's the plan for supervised learning setup. So again, we want to learn how to generalize a function from examples. So given an input, given a novel input, we want to train a system to estimate that output in a reliably correct way. That's the goal. So how do we do this? Well, there's a few steps that we follow. The first step we've already done here, which is we have to gather some data. So gather labeled data. And what I'll call this, maybe just I'll put a little bit of notation on it. I'll say D, which is it's a set of the actual data, which I'll call X, and the labels, which I'll call L. So X is the data points, and L is their labels. So we got to have some examples to learn from. Okay, second step is we also need a collection of functions to choose from. Sometimes people call this the machine learning model. So we need a space of functions, and I'll call it maybe script F, to choose from, or from which we can choose a function to fit the data. Okay, so we do have to fix possible functions that we can think of. And that's a bit abstract, but I'll show you an example up here in a moment. And then finally, we need a way of storing. So devise a way of scoring a particular function choice, F, for how well it fits the data. We use something called a loss function to do this. This is really, you would have called this in Calc 1 or Math 111, and it's just an objective function. So an objective function, and I will call this script L. So we come up with something called a loss function. The loss function is minimized when our particular function choice best fits the data. Okay? So the best possible function that I can possibly pick for my space of functions will minimize my loss function. So that's just a little notation I put on the plan here, but yeah, 3-point plan. Gather my data. Come up with a set of functions that I'm going to allow you to think about applying to the data. And then finally, come up with a loss function, another function, to score how well a particular function works on fitting our data. And so in general, you can write the scheme of what we're trying to do in supervised learning as trying to find the function. So I'll say, we're looking for a function, I'll call it f star for the optimal function that we're searching. So we're saying f star was going to be the argmin over all functions in our function space of the loss function applied to this particular function under consideration and tested out on the data. So we overall possible functions applied to the data. We want the one that minimizes this loss function. All right? Okay, so let me pause there for a second and let that sink in, and then we'll continue.